So, good morning, everyone. This is the second lecture, revision lecture of Unit 3. Okay. So, in lecture 1, what we have studied? We have studied what is hydraulic machine, what is hydraulic turbine, general layout of hydroelectric power plant, definition of head and efficiency. We have seen various head, that is gross head and net head, and efficiencies, that is hydraulic efficiency, mechanical efficiency, overall efficiency, and volumetric efficiency. We have derived the formula for the same. We have established the relation between the three efficiency, that is mechanical, hydraulic, and overall efficiency. After that, we have seen the classification of hydraulic turbine, that how hydraulic turbine is classified on four distinct levels, the four basic criteria. Okay. On the basis of that, we have seen impulse turbine, reaction turbine, we have seen tangential flow turbine, radial flow turbine, axial flow turbine, and mixed flow turbine. We have seen high head, low head, medium head turbine. We have seen low specific speed, high specific speed, and medium specific speed turbine. In the second lecture, today's, we will learn about the first type of turbine, that is Pelton wheel, which is in your syllabus. Next, we will see the construction of Pelton wheel. Next, we will study the working of Pelton wheel, how it works. Then the velocity triangle of Pelton wheel. And if time permits, we will see some numericals as well. Okay. So let's start with Pelton wheel. So what is Pelton wheel? Pelton wheel is a tangential flow impulse turbine. See, these two words are very important, tangential flow and impulse turbine. It defines the whole criteria of Pelton wheel. So tangential flow means when the jet of water emerge from the nozzle, it will remain tangent to the wheel. It will remain tangent to the rotor. Okay, so that is why it is called tangential flow turbine. And impulse turbine means that at the inlet of the turbine blade and at the outlet of the turbine blade, pressure will remain constant and it is equal to the atmospheric pressure. That is, the jet have energy equivalent to the kinetic energy only. There is no pressure energy associated with it. This is called impulse turbine. So here we have seen why it is called tangential flow impulse turbine, because the jet will remain tangent to the rotor. It is called tangential flow turbine and the energy is associated with kinetic energy. The jet has energy associated with kinetic energy, and the inlet pressure and the outlet pressure is remain same, and that is equal to atmospheric pressure, and that is why it is called tangential flow impulse turbine. This turbine is used for high head, means when there is a net head is very high, then only we can use Pelton wheel. For low head, we cannot use this Pelton wheel, Pelton turbine. Okay, it is named after an American engineer, L.A. Pelton, who had discovered this turbine, or who had designed this turbine. Okay, so this is a small introduction about So this is the working of jet. This is the working of Pelton, complete working of Pelton wheel. What are the important components? Nozzle, runner with bucket, casing, and braking jet. Okay. Next is velocity triangle. What is velocity triangle that we have already seen in unit 2? It will be similar to that. So before going to the velocity triangle, we must know what will be the design. What is the design of this Pelton wheel bucket? Okay, so this is the design of Pelton wheel bucket. It is mounted on the rotor. You can see that there is a rotor here. It is mounted like this, and this center portion, this line is called splitter. The water jet from the nozzle strikes on this splitter, and half of the water go in this way and half of the water go like this, and it will create impact on this bucket, and this bucket start to rotate. Okay, so this is the design of this Pelton wheel bucket. If we want to have a clear picture, more clear picture, the design will be like this. Water from the nozzle coming like this with this direction, coming jet is like this, and we will strike the splitter that on the tip of this splitter, and the water will move like this, and this bucket will start moving. It can rotate, it is mounted on the rotor, so it can rotate only, so it start rotating. Okay, so here the velocity v1 is the velocity of jet when it before it strike the bucket, and after striking the bucket, the direction changes, and it is coming out of the bucket with a velocity v2. So with this concept, we will go for velocity triangle. So there are certain nomenclatures that we have to keep in mind. This D star is the diameter of penstock. Okay, this capital D is the diameter of Pelton wheel. This Pelton wheel diameter, and is the speed of wheel in RPM, the speed of the bucket, yeah, the speed of the wheel with which it rotates, and small d is the diameter of this jet. Okay, so with this we'll start our velocity triangle. So this is the basic velocity triangle of Pelton wheel. This is very simple as compared to the steam turbine that we have studied. This is in this splitter where the water gets inlet to the bucket. Here we will draw inlet velocity triangle, and from where it comes out, we draw it here outlet velocity triangle. So first we will see inlet velocity triangle. Okay, but before going into this, we have to know two important terms. First one is jet velocity, and second one is blade velocity. So what is jet velocity? Jet velocity, at what velocity jet is coming out. Okay, and blade velocity, the tangential velocity of the blade. So as we have seen that entry and exit of the jet from the bucket during this process, the distance of jet from the center will remain same. It will not change, and that distance, and we know that tangential velocity is a function of RPM and diameter of wheel. So inlet blade velocity and outlet blade velocity will be given as pi dn by 60, and it will remain same because inlet and outlet of jet is at the same distance from the center of the rotating axis. Okay, so u1 and u2 will remain same, that is pi dn by 60. Now second is velocity of jet. How the velocity of jet is calculated? It will depend upon the available head. That whatever head will be available, it will convert it into kinetic energy. That potential energy is converted into kinetic energy. So H is equal to V. What is kinetic energy? V1 square by 2G. Okay, so we'll talk about per unit mass. Half mv square hota hai kinetic energy. If we will talk about per unit mass, it will be half V square by 2G in terms of head. That will be equal to capital H. So transferring and keeping V1 at one side, will get velocity of jet as under root 2G H. So in this is the two important terms, that is blade velocity and jet velocity. It will remain same. The formula for blade velocity will be pi dn by 60, and the formula for jet. So let's come to velocity triangle at inlet. We are seeing that at inlet velocity triangle is a simple straight line. एक सिंपल स्ट्रेट लाइन रहेगी वेलोसिटी ट्रायंगल, ठीक है. तो जो v1 रहेगा इट विल बी कंप्लीटली ट्रांसफर टू द टेंजेंशियल वेलोसिटी बिकॉज इट इज टेंजेंट टू द बकेट एंड दिस v1 विल बी इक्वल टू vw1. क्योंकि पूरी की पूरी जो काइनेटिक एनर्जी है इट विल बी कन्वर्टेड टू रोटेट द प्लेट, पूरी की पूरी यूटिलाइज हो रही है, सो दैट vw1 विल बी इक्वल टू v1 and VR1 relative velocity. If we assume that the bucket is moving with a tangential velocity of u1, so relative velocity will be v1 minus u1. It can also be written as vw1 minus u1. So that relative velocity at inlet will be v1 minus u1, and we have seen that tangential velocity will remain same. So u is equal to u1 is equal to u2. So it can be written as u. Here the jet angle and blade angle is 0. Alpha and theta will remain 0 because we are getting a straight line as an inlet velocity triangle. Okay, so this is about inlet velocity triangle, which is very simple. We have to just remember these two things, that tangential velocity or velocity of world component will be equal to the jet velocity, and relative velocity is the difference between jet velocity and blade velocity. And we have seen that how to calculate this velocity of jet and blade velocity. Now from outlet velocity triangle, it will be like that the jet coming out of this portion of the bucket with a relative velocity Vr2, blade velocity will remain u2. This v2 jet velocity outlet will be less than relative velocity because the direction of jet has been changed. So we will get outlet velocity angle like this, where outlet jet angle is beta 2 and outlet blade angle is phi. Okay, so we will get this type of outlet velocity triangle that we have already seen in case of steam turbine. This is similar to. I think there is a net problem here. No issue. We'll continue. So from outlet velocity triangle, if there is no frictional loss in the blade, then what is the outlet relative velocity will be equal to the inlet relative velocity. That is, VR1 will be equal to VR2, and VW2 will be given by this length, can be seen here, minus U2. So this is the cos component of VR2. So VW2 can be written as VR2 cos phi minus U2. Okay, so this is the two formula that is very important in case of outlet velocity triangle, that is VR2 equal to VR. If there is some blade frictional loss is given, then there will not be an issue. We have to consider that while calculating VR2, and VW2 will remain like this, that VR2 cos phi minus U2. VR2 cos phi is this line complete, minus if you subtract U2 we will get VW2. We are in interest for calculating VW1 and VW2 that we have seen that for calculating the force developed by the jet, we have to know the tangential component of the velocity. Now, what will the force develop? Force develop will be the mass of water striking per second into initial velocity with which jet strike in the direction of motion minus final velocity of jet in the direction of motion. It comes from the Newton's second law of motion. Okay. So again, initial velocity is Vr1. We have to consider relative velocity. So initial velocity is Vr1, which is equal to Vw1 minus u, that we have seen it from inlet velocity triangle, and component of relative velocity at outlet in the direction of motion. So this is at some angle phi. So we have to consider in this direction, in horizontal direction. So VR2 cos phi is the direction that is horizontal to this, and it is in the opposite direction. So by keeping minus sign and considering that VR1 is equal to VR2, we are writing is minus VR1 cos phi. Okay, minus sign because this is the direction of jet is opposite at inlet and outlet. They are in opposite direction. And VR1 again we know that it is equal to VW1 minus U1. So completely we can write it as minus VW2 plus U into cos phi. Okay. So Fx can be written as mass of water striking per second can can be given by rho into A into V1, VR1 from here VW1 minus U, and this is from minus this minus VR1 cos phi can be written as minus U plus VW2. U2 plus VW2, U2 can be replaced as U. Now, while we open the bracket, this minus minus will become plus, so that this U will get cancelled out and will remain with rho into A into V1 into VW1 plus VW2. So this is the final formula for the amount of force developed when the jet strikes the bucket. Now there are three cases arise. This formula is applicable when this beta has some acute angle. Okay. Once the beta angle increases and it increases up to 90 degree, then what will happen? This VW2 will become 0. Okay. So from this formula, VW2 will be vanishes. So there are three cases. First, when beta is less than 90 degree, the formula that we have derived will be applicable to calculate the force developed. When beta is equal to 90 degree, this VW2 will become 0. Okay. So here it is wrongly written. It will be rho into A into V1 into VW1. And when this beta will become less than 90 degree, what will happen? This beta will become obtuse angle more than 90 degree, then there will be a negative sign because the direction will become opposite. So there are three cases. Once when the beta is acute angle, it will be VW1 plus VW2. Once when the beta is 90 degree, VW2 will become 0. And once when beta is greater than 90 degree, VW2 will become negative. It is in the opposite direction. This V2 will be like this, V2 will be like this, and VW2 will, we have to take minus sign with minus sign. Next, work done. Work done, we know that work done is a work done by the jet on runner per second will be Fx into U. We have to multiply force developed by U and we'll get work done. The unit will be force unit is Newton and velocity unit is blade velocity unit meter per second. So it will be rho A V1 VW1 plus VW2 into U. Again, this formula will change according to the value of beta. If beta is less than 90 degrees, this formula is applicable. If it is equal to 90 degrees, VW2 will not be there. And if it is greater than 90 degrees, there will be a minus sign. Now, power given to the runner by jet, we have to divide it by 1000 okay, per second, and we will get the power given to the runner by the jet. Okay. Now, there is an important term which will come when we solve numerical, that work done per second. This is work done per second. Now it is asking to calculate work done per second per unit weight of the fluid striking per second. So we have to divide this work done per second by weight of fluid striking per second. So what is the weight of fluid? This is the mass of fluid, rho A into V1. If we multiply mass into G, we will get weight. So rho A V1 into G is the weight of water striking, divided by time will get weight of fluid striking per second. So this is calculated like this. Okay, rho A V1 into G, and what will be the unit of this? The unit will be meter. Okay, because you can calculate here this rho A V1 will be cancelled out. This will give meter square. This is meter per second. This is meter per second. Combinedly, it will give meter square per second square. And here the velocity of unit of gravitational acceleration is meter per second square. So the completely it will give the unit meter. Okay, so this is the work done per second per unit weight of fluid striking per second, and its unit is meter. So work done in terms of head. Okay. Next, some important point related to Pelton wheel. So, velocity of jet at inlet, we have seen that V1 is equal to under root 2gs, but it is not always the case. Sometimes coefficient of velocity is given, so we have to multiply this root 2gs with CV, that is coefficient of velocity, whose value varies from 0.96 to 0.99. Next will be the velocity of wheel. Velocity of wheel will be equal to phi into under root 2gs, where phi is the speed ratio, whose value varies from 0.43 to 0.42. This phi is speed ratio. Generally, what is given in the numerical, it is given net head and coefficient of velocity and speed ratio. So with these two formula, we can easily calculate the velocity of jet and blade velocity with these two formula. The angle of deflection of the jet through the bucket is taken as 165 degree. The angle of jet, the angle of deflection, what is angle of deflection? Let us see from this diagram. Angle of deflection is this. This is the angle of deflection, because jet enter in a tangential direction, it will reverse back following this path. So this is the angle of deflection. When we extend this VR2 line which meet this horizontal line, this is called angle of deflection, and with this angle of deflection the value of phi is calculated. This complete angle is 180 degree. So when we subtract angle of deflection from 180 degree from angle of deflection, we will get this angle, and this angle is equal to the phi as alternate opposite angle. Okay, so like this, if angle of deflection is given, we can calculate the value of phi by subtracting angle of deflection by 180 degree. Okay, so if it is not given in the question, we have to take it as 165 degree. Next is the mean diameter or pitch diameter d of the Pelton wheel. We know that u we have calculated by using this formula, but u is also pi d n by 60. Okay, tangential velocity is given by pi d n by 60. So by keeping d on one side and keeping the rest of the thing on the other side, we can calculate the diameter of the wheel. Jet ratio is the ratio of wheel dia to the jet dia. There is an important term, jet ratio, which is equal to the diameter of the wheel, which is calculated from here, and diameter of jet, small d is diameter of jet, which is generally equal to 12 in most of the cases. Next is number of bucket. How much number of bucket or how much number of blade which is required in Pelton wheel can be calculated like 15 plus 0.5 into m. M is d by d. Okay. Number of jet is obtained by dividing the total flow rate. Now there can be a multiple jet Pelton wheel or single jet Pelton wheel. The number of jet can be calculated by total rate of flow through the turbine by the rate of water through a single jet. Okay, capital Q by small q. While designing the Pelton wheel, if there is a problem that it is asking to design a Pelton wheel. Okay, so what we have to design in Pelton wheel, what actually it is asking? It is asking diameter of jet. If it is given that design a Pelton wheel, so what we have to calculate? We have to calculate the diameter of jet, that is small d, diameter of wheel, that is capital D, width of bucket, that is equal to 5 into small d. Once we calculate the diameter of jet, when we multiply it by 5, we'll get the width of the bucket. Next is depth of the bucket. How much depth the bucket should have? It is 1.2 into d. See, all these things depend upon the diameter of jet. Okay, so width of bucket is 5 times that of diameter of that. Depth of bucket is 1.2 times that of diameter of jet. Next is number of bucket that already we have seen. The formula, with that formula we will calculate the number of bucket, and size of bucket means the width and depth. So if it is in a problem, it is saying that design a Pelton wheel, so we have to calculate this 5 things. Okay, small d, capital D, width, and okay. So this is what I have to discuss in today's class, the theory. Let us compile it. So what we have seen in today's class, we have seen Pelton wheel. What is Pelton wheel? What are the important components of Pelton wheel? That is nozzle, runner, casing, and braking weight. We have seen the layout and its working, how it works. Next, we have seen the design of blade, what type of blade is used in, what type of bucket is used in Pelton wheel. Then we have seen the velocity triangle, and we have understand that the inlet blade velocity and outlet blade velocity will remain same because its distance from central is constant. Then we have seen that velocity of jet will be under root 2 gs because there is only kinetic energy associated in Pelton wheel. Next, we have seen the velocity triangle. Inlet velocity triangle, we get VW1 and VR1, and we have seen that alpha and theta are 0. From outlet velocity triangle, we get VW2 is equal to VR1, VR2 is equal to VR1. It is when there is no friction in the blade. If it is given that there is a friction in the blade and there are some percentage loss, then we have to consider that. Then in that case, VR2 will be obviously less than VR1. And VW2 we have calculated from the geometry, that is VR2 cos phi minus U2. So then we have calculated the force developed by the jet, and that force developed by the jet depend upon the angle beta. If it is acute angle, we'll get rho a V1 VW1 plus VW2. If it is 90 degrees, what we will get? We will get VW1 only and VW1 minus VW2 when it is obtuse angle. Then work done multiplying by U, power given. This is important term that I have seen, that work done per second per unit weight of the fluid striking the fluid. Then we have seen some important point related to Pelton wheel, and then we have seen the design, what are the design criteria for Pelton wheel. So this is for the today's class. There is some network issue, but I hope you will understand. You have understand this. Nikhil, you can unmute yourself, and
Yes, sir.
I hope you understand something.
यस सर, सब समझ में आया, बट सर बीच में सर थोड़ा प्रॉब्लम हो रहा था सर,
हाँ,
इंटरनेट
थोड़ा
के कारण।
थोड़ा थोड़ा हो रहा था, कोई इशू नहीं है। नेक्स्ट क्लास
यस
अपन
सर,
लेंगे, तो समझ में तो आया ना?
यस सर, आया सर, पूरा आया सर।
अरे